Every photon in the night sky is a message from the distant past. We are about to decode 30 of the most profound enigmas carried within that ancient light. This is a journey across time and space to confront the cosmic puzzles that defy our current understanding of the universe. You will gain a new perspective on reality itself, seeing the cosmos not as a static picture, but as a dynamic story written in radiation. We will explore a mysterious drift of entire galaxy clusters and investigate a star that dims in inexplicable ways. What hidden truths about existence are waiting to be uncovered in the oldest light? The story of our cosmic investigation begins with a persistent, unexplained hiss. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were calibrating a sensitive horn antenna in New Jersey, aiming to listen to distant galaxies. Yet no matter where they pointed their instrument, a faint, uniform static permeated their readings. They meticulously cleaned the antenna, even evicting a pair of nesting pigeons, but the ghostly signal remained. This was not a technical fault. It was the echo of creation itself, the cosmic microwave background, the oldest light we can ever hope to see. This radiation is the cooled remnant of the universe's fiery birth, a snapshot taken when the cosmos was a mere 380,000 years old. Before that moment, the universe was a hot, dense fog of particles and light, opaque and searing. As it expanded and cooled, atoms finally formed, and light was set free to travel across the ages. The cosmic microwave background is that light, stretched by the expansion of space over 13.8 billion years into the microwave part of the spectrum. Its discovery was a monumental, accidental confirmation of the Big Bang theory, earning Penzias and Wilson the Nobel Prize. For cosmologists, this faint glow is a celestial treasure map. Its most astonishing feature is its near-perfect uniformity. No matter which direction you look, the temperature of this ancient light is almost exactly the same, a chilly 2.7 degrees above absolute zero. This uniformity tells us the infant universe was incredibly smooth and homogeneous, a fact that itself poses a deep mystery about how such a vast region could have reached this equilibrium. But perfection is not the whole story. Embedded within that smooth sea are tiny, vital imperfections, fluctuations in temperature of just 1 part in 100,000. We call these anisotropies. They are the cosmic equivalent of a whisper in a silent room. These minute ripples in density imprinted on the light are the primordial seeds of all structure in the universe. They are the gravitational blueprints from which everything we see eventually grew. Slightly denser regions marked by slightly cooler spots in the cosmic microwave background pulled in more matter over billions of years. Under the relentless pull of gravity, these seeds blossomed into the first stars, then galaxies, then the vast clusters and filaments of the cosmic web. Satellite missions like Planck have created exquisitely detailed all-sky maps of this ancient light, showing a mottled, almost artistic pattern of hot and cold spots. That map is not just a picture of the past, it is a frozen moment that contains the entire future. Every galaxy, every star, and by extension, every one of us, owes our existence to those specific, minuscule fluctuations in the universe's first light. This echo is not just a relic, it is the first chapter of our origin story, written in the cold, faint glow of microwaves. Yet within this seemingly perfect map of the infant universe, cosmologists began to notice something unsettling. The cosmic microwave background is not as flawless as it first appeared. It contains strange, subtle features, anomalies that stubbornly refuse to fit the neat predictions of our standard model. These are not the tiny ripples that seeded galaxies. These are larger, more peculiar patterns that hint at a cosmos far stranger than we ever imagined. The first of these great mysteries is known simply as the cold spot. In the southern sky, there exists a region of the cosmic microwave background that is significantly colder and far larger than our theories can comfortably explain. It spans a vast area about 1.8 billion light-years across. According to our standard understanding, such a colossal cold patch should be an extreme statistical rarity, a 1 in 50 chance at best. Some researchers argue it could just be a cosmic coincidence, a random fluctuation in the data, but others propose a far more thrilling possibility. What if the cold spot is a bruise, a scar from a collision with another universe? In a speculative model known as the multiverse, our universe is one bubble among infinite others in a greater cosmic foam. If, during its earliest moments, our expanding bubble universe brushed against a neighboring one, the energy of that collision could have left an imprint on the cosmic microwave background, a cold, circular shadow exactly like the one we see. While this idea remains highly controversial and far from proven, it illustrates the profound stakes of this mystery. The cold spot forces us to ask whether we are truly alone in existence or merely one reality in an endless, frothing sea of them. An even more fundamental challenge to our cosmic principles is known, rather dramatically, as the axis of evil. This anomaly refers to an unexpected alignment in the larger scale patterns of the cosmic microwave background. The universe, according to the bedrock principle of isotropy, should have no preferred direction. It should look roughly the same in all orientations. Yet the data suggests the opposite. The warmer and cooler fluctuations on the larger scales appear subtly aligned along a particular axis in space, as if the universe itself has a tilt. This is deeply problematic. It is like drawing a map of the Earth and finding all the continents inexplicably lined up along a single line of longitude. The most conservative explanation is, again, a statistical fluke or an unknown systematic error in our measurements. But if it is real, the implications are staggering. It could point to a pre-existing structure from before the Big Bang, a shadow of a prior cosmic era imprinted on our own. It might suggest the universe has a complex, finite shape, a cosmic topology where space wraps around itself in unexpected ways, creating patterns that seem to orient in a specific direction. These anomalies, the cold spot and the axis of evil, are more than just data points. They are cosmic whispers from the edge of our understanding. They keep cosmologists awake at night because they represent either the limits of our current models or the first faint cracks in our picture of reality, through which we might glimpse an entirely new cosmology. But the anomalies are not confined to the ancient light of the cosmic microwave background. They are happening right now in the motion of our own cosmic neighborhood. Our Milky Way galaxy is not drifting aimlessly through the void. It is racing along with thousands of other galaxies toward a specific point in the darkness, pulled by a gravitational force so immense it defies what we can see. This is the mystery of the Great Attractor. Astronomers first detected this colossal pull not by sight but by deduction. By mapping the motions of galaxies across vast distances, they noticed a disturbing river-like flow. Instead of moving apart uniformly with the expansion of the universe, entire clusters of galaxies, including our own local group, were streaming toward a region of space in the constellation Centaurus. It was as if someone had pulled a cosmic drain plug and everything was sliding toward it. The force required to orchestrate this grand motion is staggering, equivalent to the pull of tens of thousands of Milky Ways. Yet when we looked toward that point in the sky, we saw nothing that could possibly account for such power. The core of the mystery lay in its location. The Great Attractor sits almost directly behind the dense, dusty plain of our own galaxy, an area astronomers call the zone of avoidance. Our view is like trying to peer through a dense, glowing fog. The stars, gas, and dust of the Milky Way's central disk completely obscure the optical light from anything behind it, hiding the source of this immense gravitational pull. For decades, it was a ghost, felt but not seen. To solve this, astronomers had to use different eyes, space telescopes like NASA, Spitzer, and WISE, which observe in infrared light, can peer through that obscuring dust. What they revealed was a monumental structure, a massive concentration of mass known as the Norma Cluster. This is a dense knot of galaxies, a galactic metropolis containing thousands of members, all bound together by gravity. It is an undeniable source of immense pull, but here is the puzzle. Even the colossal mass of the Norma Cluster, while significant, does not seem to fully account for the scale and speed of the galactic river we are caught in. The motion suggests there is even more mass hidden behind it, pulling on the Norma Cluster itself. This points to something even grander, a deeper gravitational anchor in the cosmic web. The Great Attractor may not be a single object, but rather the heart of a far larger superstructure, a junction where several titanic filaments of the cosmic web converge. We are being pulled not just by a cluster, but by the accumulated weight of an entire sector of the universe, a shadowy concentration of dark matter and galaxies that we are still struggling to map. So the mystery evolves. We have found a piece of the puzzle in the Norma Cluster, but the full picture remains shrouded behind the veil of our own galaxy. The Great Attractor teaches us a humbling lesson about our place in the cosmos. We are not stationary observers. We are participants in a vast, dynamic flow, caught in a current whose ultimate source still lies hidden in the darkness. But the cosmic river does not end with the Great Attractor. The flow appears to stretch even further, pointing toward something beyond our horizon. In 2008, a team of astronomers made a startling announcement. They had studied the motion of over 1,000 galaxy clusters, each containing thousands of galaxies, using a clever technique called the kinetic Sunyaev-Zeldovich effect. This method allows scientists to detect the subtle imprint of moving clusters on the ancient cosmic microwave background. What they found was not random motion. These colossal structures, scattered across billions of light-years, were all streaming in a coherent direction at speeds exceeding 2 million miles per hour. They called this phenomenon dark flow. The name is deliberate, echoing the mysteries of dark matter and dark energy. Like those enigmas, dark flow cannot be explained by the gravitational pull of any visible structure within our observable universe. The Great Attractor is powerful, but its influence has limits. Dark flow suggests that something even more immense is tugging on these clusters, something that lies beyond the cosmic horizon. This is a profoundly radical idea. According to standard cosmology, the observable universe is everything we can possibly see or interact with, a sphere about 93 billion light-years across, limited by the distance light has had time to travel since the Big Bang. Nothing from outside that bubble should be able to affect us, as no information can travel faster than light. Yet dark flow hints that the gravitational influence of colossal masses outside our bubble is somehow reaching in. How is that possible? The leading hypothesis involves the very nature of the Big Bang itself. If, in its first infinitesimal fraction of a second, the universe underwent a period of hyper-rapid expansion called inflation, then the observable universe is just a tiny patch of a much grander, perhaps infinite, whole. In that infinite landscape, there could be regions of vastly different density. Imagine our universe as a calm valley, but just over a mountain range lies a titanic, unseen continent. The gravitational pull from that external, supermassive structure, though its light can never reach us, could still have been imprinted on the fabric of space-time during inflation, setting our entire local region into motion. The debate around dark flow is intense. Some scientists question the data analysis, suggesting statistical errors or unknown foreground effects from our own galaxy. Others are searching for confirmation with newer, more precise data from observatories like the Planck satellite. The results so far remain inconclusive, keeping this mystery alive. If dark flow is real, its implications are almost incomprehensible. It would be the first observational evidence that our cosmos is part of a multiverse, or at the very least a structure of unimaginable scale. We would have to accept that we are not just drifting toward a hidden attractor within our universe, but that our entire cosmic neighborhood is sailing on a current whose source lies in another realm entirely. The flow of galaxies hints at structures of unimaginable scale, but what if the most shocking structure is not an assembly of matter, but an absence of it? Drifting through the constellation of Boötes, there exists a region of space so profoundly empty it has earned the name the Great Nothing, or the Boötes Void. This is not a simple gap between galaxies. It is a spherical chasm in the cosmic web, a staggering 330 million light-years across. To grasp that scale, if our Milky Way were placed at the dead center of this void, the night sky would be a desolate expanse. We would not have discovered another galaxy until the 1960s, when our telescopes finally became powerful enough to peer beyond its terrifying borders. In a universe defined by the intricate web-like structure of galaxy clusters and filaments, the Boötes Void is a cosmic desert of almost incomprehensible proportions. While it is not completely empty, surveys have found only about 60 galaxies scattered throughout its immense volume. In a region of space that size, you would normally expect to find many thousands. Those few galaxies that do exist within the void are like isolated islands in an ocean of nothingness, separated by distances so vast their night skies would be almost starless. How does such a colossal nothing come to be? One leading theory suggests it is the result of smaller voids merging over billions of years. As the universe evolved, gravity pulled matter into filaments and clusters, leaving behind expanding bubbles of emptiness. Over time, these smaller bubbles could have coalesced like soap films merging to create a single gigantic void. This fits within our standard models of cosmic structure formation, though the sheer size of the Boötes Void pushes those models to their limit. More speculative ideas reach back to the universe's first moments. Could a massive quantum fluctuation in the density of the primordial universe have created a seed for such emptiness? Or, in a truly mind-bending possibility, could it be evidence of something else entirely? Some have wondered, purely as a thought experiment, if a void of this scale could be the result of astroengineering on a level beyond our imagination. The concept, known as a Dyson sphere, or more accurately a Dyson swarm, involves an advanced civilization capturing all the energy output of its star. What if not one star, but an entire galaxy's worth of stars were encapsulated? From a distance, such a galaxy would vanish from the visible spectrum, appearing as a dark void. While there is absolutely no evidence to support this as an explanation for the Boötes Void, and it remains a fringe speculation, it underscores how profoundly alien such a structure appears. It challenges our understanding of how the universe organizes itself. The void is a stark reminder that the cosmos is not uniformly filled. It is a tapestry of dense clusters and vast, echoing vacancies, and within those vacancies may lie clues to the most fundamental forces that shaped everything. The echoing voids of space are defined by absence, but some mysteries announce themselves with a frantic, irregular flicker. In the constellation Cygnus, a star designated Cassini 8462852, now famously known as Tabby's star, behaves like no other. Data from the Kepler Space Telescope revealed its light did not dip in the gentle, predictable rhythm of an orbiting planet. Instead, it plunged erratically, sometimes by as much as 22%, in sharp, asymmetrical patterns that lasted for days or weeks before returning to normal. This was not a single object passing in front of the star. It looked like a vast, chaotic swarm of something blotting out its light. The scientific community erupted with possibilities, a perfect case study in how cosmic detective work unfolds. The initial, most tantalizing hypothesis came from the realm of science fiction. Could these be the shadows of a megastructure, the concept of a Dyson sphere, a hypothetical swarm of energy collecting satellites built by a civilization far more advanced than our own, fit the bizarre data all too well? It was a captivating narrative, a signal of intelligence in the cosmos. Yet scientists are trained to exhaust the natural before invoking the extraordinary. Other explanations flooded in, perhaps a massive family of comets shattered by a close encounter with the star was creating a dense, irregular cloud of ice and dust. Maybe it was circumstellar debris from a catastrophic planetary collision, or even an immense warped ring system around a giant planet. The pursuit of an answer mobilized observatories across the globe and in space. Astronomers pointed radio telescopes toward the star, listening for the artificial buzz of technology. They found only silence. Observations across the electromagnetic spectrum, particularly in infrared light, provided the crucial clue. If solid, opaque megastructures were blocking the light, the star would dim uniformly at all wavelengths. Instead, the dimming was much more pronounced in blue light than in red. This is the classic signature of dust. Tiny particles smaller than a grain of sand scatter shorter wavelength blue light more effectively, letting the longer red wavelengths pass through more easily. The evidence now strongly suggests a natural, if spectacularly messy, explanation. Tabby's star is likely surrounded by a vast, uneven cloud of fine dust, possibly from the disintegration of a comet-like body or a family of asteroids orbiting in a clumpy, chaotic swarm. Yet the case is not entirely closed. The exact origin and nature of that dust remains puzzling. What event could have produced such an immense quantity? Why is its distribution so irregular? The star itself also shows a very long-term, gradual dimming over the past century, adding another layer to the puzzle. While the alien megastructure hypothesis has retreated, Tabby's star endures as a powerful symbol. It represents the thrilling process of science itself, where a strange signal sparks our most ambitious dreams, only to be patiently unraveled by data, leading us not to disappointment, but to a deeper, more nuanced wonder about the strange and varied phenomena our universe contains. While Tabby's star flickers with the dust of natural chaos, other signals from the depths of space are far more abrupt and violent. They arrive without warning, a single, piercing scream of radio energy that lasts only a millisecond, yet carries the power of 500 million suns. These are fast radio bursts, and they are one of the most electrifying mysteries in modern astronomy. Imagine the entire energy output of our sun, not over a year or a month, but over nearly a century, compressed into a flash of radio waves briefer than the blink of an eye. That is the staggering scale of a typical fast radio burst. These bursts travel for billions of years across the universe, stretching and dispersing through the thin haze of intergalactic plasma, until a chance alignment brings them screaming into the focus of our radio telescopes. For years after their initial discovery, each burst was a unique event, a cosmic flashbulb popping once in the darkness and then vanishing forever. This pointed to catastrophic, one-time origins, like the final death spiral of two merging neutron stars or the cataclysmic collapse of an overly massive star into a black hole. But then, everything changed. Astronomers found a repeater. A source, now known as FRB 1211-2, began firing off multiple bursts, sometimes in frantic clusters. This single discovery ruled out any model that required the complete destruction of the source. Whatever was making these bursts was surviving the event, and it was capable of doing it again and again. The hunt for an explanation narrowed to objects of immense power and durability. The prime suspect today is a magnetar, a specific type of neutron star with a magnetic field so intense it defies comprehension. A magnetar's field is a quadrillion times stronger than Earth's. If one were located halfway between Earth and the Moon, it would strip the data from every credit card on the planet. Theorists propose that these stars can experience starquakes, sudden ruptures in their rigid crusts. When the crust snaps under the strain of the unimaginable magnetic forces, it could release a titanic shockwave of energy, manifesting as a fast radio burst that echoes across the cosmos. Other theories persist, including highly energetic flares from the poles of an active black hole, or even the speculative tremors of cosmic strings, hypothetical defects in the fabric of space-time from the universe's first moments. Each new detection provides a vital clue. By using networks of telescopes to pinpoint the locations of these bursts, astronomers have traced them back to their home galaxies. They are not coming from just anywhere. Repeaters like FRB 1211-2 appear to originate from regions of active star formation, dusty environments rich in the materials that forge massive stars and the magnetars they leave behind. This galactic context is like finding a specific type of fingerprint at a crime scene, steadily building a case for a natural, if extraordinarily violent, astrophysical engine. Yet the sheer, raw power of these millisecond screams continues to baffle us. What natural process can be so efficient, so brutally focused, that it channels the energy of stars into a radio flash so brief? Every time a new burst lights up a telescope's sensors, it is a reminder of how much raw, untamed power crackles in the darkness, and how little we still understand about the most energetic engines in the universe. That single, piercing scream of a fast radio burst lasts just milliseconds, but another signal from the void lingered for a full 72 seconds. On the night of August 15, 1977, the Big Ear Radio Telescope at Ohio State University was engaged in a quiet, systematic search of the sky. Its mission was part of the search for extraterrestrial intelligence, scanning for any narrowband radio signal that stood out against the natural cosmic static. For the most part, the data printouts were monotonous, columns of numbers and letters representing unremarkable noise. But on this night, the telescope's gaze passed over the constellation Sagittarius, and the chart recorder pen leaped. The signal was so powerful, so perfectly tuned, that it overwhelmed the equipment's scale. When volunteer astronomer Jerry Amon reviewed the data printout the next day, he saw a string of characters, 6 consecutive alphanumeric readings that were off the charts. Circling them in red pen, he simply wrote one word in the margin, a spontaneous expression of pure astonishment. Wow, that annotation gave the signal its immortal name. The wow signal was everything scientists had hoped to find. It was a narrowband signal concentrated at exactly 1,420 megahertz. This frequency is profoundly significant as it corresponds to the emission line of neutral hydrogen, the most common element in the universe. It is considered a universal channel, a logical place for a technological civilization to broadcast a cosmic hello. The signal rose and fell over 72 seconds, exactly as expected for a fixed source passing through the stationary telescope's beam, peaking in intensity and then fading away. It was not a repeating pattern, not a message we could decode. It was a single, loud, unambiguous tone, as if someone had briefly keyed a cosmic microphone on the other side of the galaxy. The immediate and enduring mystery is that it was never heard again, despite numerous dedicated efforts to re-observe that precise point in the sky with more powerful telescopes. Including projects by SETI Institute scientists decades later, the signal has remained stubbornly silent. This one-off nature is what fuels both the mystery and the skepticism. If it was a deliberate broadcast, why only once? The hunt for a natural explanation has been exhaustive. One recent hypothesis pointed to a passing comet. In 2017, an astronomer noted that 2 comets, which were not known in 1977, had been in the same area of sky. Could their clouds of hydrogen gas have emitted a similar signal? The idea gained brief attention but was swiftly dismantled by other researchers. The comets were too faint, and the hydrogen they released does not produce a narrowband signal of such staggering intensity. Other possibilities include a glinting satellite or space debris reflecting a terrestrial transmission back to Earth, but the specific frequency and the beam shape of the Big Ear Telescope make such a chance alignment highly unlikely. Each proposed natural cause seems to have a fatal flaw, leaving the signal in a tantalizing limbo. It was too perfect to be easily dismissed, yet too singular to be confirmed. The WOW signal stands as the quintessential SETI anomaly, a ghost in the machine of cosmic listening. It is not proof, but it is a powerful possibility. It embodies the profound frustration and hope of the search. For 72 seconds, the universe seemed to speak directly to us, and then it returned to an infinite, enigmatic silence, leaving behind a single, handwritten word that captures the essence of our cosmic curiosity. The WOW signal remains a haunting whisper in the static, a one-time event that defies easy explanation. Yet some cosmic mysteries announce themselves not with a shout, but with a persistent, nagging drift, measured in increments smaller than a snowflake's weight. This is the strange tale of the Pioneer anomaly. Launched in the early 1970s, the Pioneer 10 and 11 spacecraft were true trailblazers. After their historic missions to Jupiter and Saturn, they continued on ballistic trajectories, becoming humanity's first emissaries on a one-way journey out of the solar system. For decades, scientists at NASA, a deep space network, tracked their faint radio signals with exquisite precision, using the Doppler effect to measure their speed and position across billions of miles. It was in this meticulous data that a tiny, stubborn discrepancy emerged. Both spacecraft, as they traveled into the outer darkness, were experiencing a minuscule but constant acceleration back toward the Sun. It was as if a faint, unseen hand was ever so gently applying the brakes, pulling them backward by about 10 billionths of a meter per second squared. This was not part of any plan. Gravity from known planets had been accounted for. The drag of the solar wind was far too weak. For years, this anomaly fueled intense speculation and even wilder theories. Could it be evidence of a flaw in our understanding of gravity itself? Perhaps Einstein's theory of general relativity needed a slight modification at the vast scales of the solar system. Some wondered if it was the gravitational pull of unseen dark matter concentrated near the Sun, or even an effect of the spacecraft moving through a subtle cosmic medium. The mystery persisted for over 2 decades, a testament to how precisely we can track objects in the deep void. The ultimate solution, however, came not from rewriting physics, but from an exhaustive accounting of the spacecraft themselves. A team of researchers launched a monumental detective effort, recovering decades-old engineering documents, telemetry data, and even original design schematics to build a complete thermal model of the Pioneer probes. Their conclusion was brilliantly mundane. The spacecraft were powered by radioactive thermoelectric generators, which produced heat as a byproduct of generating electricity. This heat radiated away into space. Crucially, it did not radiate evenly. More heat escaped from the rear of the spacecraft, where the power units were mounted, than from the front. This anisotropic, or directionally uneven, thermal radiation created a tiny but constant thrust, exactly like a very faint photon rocket. The photons carrying heat away from the craft imparted a minute push in the opposite direction, which was precisely back toward the Sun. Once this effect was meticulously calculated and included in the trajectory models, the anomalous acceleration vanished. The Pioneer anomaly was solved. This story is a profound lesson in cosmic humility. It highlights the incredible precision of modern science, where we can measure effects equivalent to the gentle pressure of sunlight on a car's surface across interstellar distances. It also underscores a fundamental principle. In the quest to discover new physics, you must first eliminate every last mundane possibility, no matter how subtle. The universe whispers its secrets in the faintest of signatures, and sometimes the answer is not a new law of nature, but a forgotten detail of our own ingenious and slightly lopsided creations. Our own planet holds a climate mystery as profound as any distant anomaly. For billions of years, the Sun has been the steady engine of life on Earth. But according to our most robust models of stellar evolution, this was not always the case. In its youth, our Sun was significantly dimmer, shining with only about 70% of its current brilliance. This presents a chilling paradox. If the young sun was so faint, solar energy reaching the early Earth would have been too weak to keep the oceans liquid. Our planet should have been a global icehouse, a glittering snowball hurtling through space, its water locked in permanent glaciers from pole to pole. Yet the geological record tells a completely different story. We have ancient rocks, some nearly 4 billion years old, that show clear signs of being shaped by liquid water. Rippled sediments, minerals that only form in aqueous environments, and even the earliest fossilized traces of microbial life all testify to a world that was warm and wet, not frozen solid. This contradiction is known as the faint young sun paradox, and it forces us to question what kept our infant planet cozy. The leading explanation points to Earth's early atmosphere, which was likely a vastly different blanket than the one we breathe today. Scientists propose it was much thicker and rich in powerful greenhouse gases like carbon dioxide and methane. These gases act as an insulating layer, trapping infrared heat that would otherwise escape into space. A dense cocktail of them could have provided the necessary extra warmth to compensate for the sun's faint glow, creating a planetary greenhouse effect strong enough to defy the ice. Another factor could have been Earth's reflectivity or albedo. With fewer continents exposed and perhaps different cloud cover, the young Earth might have absorbed more sunlight rather than bouncing it back into space. There are even speculative ideas that the young sun, though fainter in total output, might have been more magnetically active, with fierce flares and ultraviolet radiation that could have interacted with the atmosphere in complex warming ways. Solving this ancient puzzle is not just about our past, it is a crucial guidebook for our future searches. As we point our telescopes at distant exoplanets orbiting other stars, we use models to judge their potential habitability. A planet lying in what we call the habitable zone, the orbital region where liquid water is possible, might not be habitable at all if its star is young and faint. Conversely, a planet slightly outside the standard zone might be warmed by a thick greenhouse atmosphere, just like early Earth. The faint young sun paradox teaches us that habitability is not a simple equation of distance from a star. It is a delicate, dynamic interplay between stellar evolution, atmospheric chemistry, and planetary geology. Our own world's mysterious past is the key that unlocks the potential for life on countless others. Earth's ancient climate puzzle reveals how fragile the conditions for life can be, a balance that extends far beyond our own atmosphere to the very edges of our celestial neighborhood. Out there, in the profound darkness where the sun's light is a mere pinprick, two vast and elusive structures are suspected to shape the destiny of our solar system. The first is the Oort cloud, a theoretical shell of frozen relics that marks the true frontier of our sun's gravitational domain. Imagine a sphere of icy rubble beginning roughly 2,000 times farther from the sun than Neptune and extending outward for perhaps a light year or more. This is not a place we can see or visit. Its existence is a necessary deduction, the only logical source for the long-period comets that occasionally plunge into the inner solar system from random directions. These cosmic icebergs, like the famous comet Hale-Bopp, take thousands or even millions of years to complete a single orbit. Their trajectories tell us they originate from a vast, diffuse reservoir, a deep freeze where primordial chunks of ice and rock have lingered since the solar system's birth. The Oort cloud is the solar system's attic, storing the unused building materials from our formation, and its gravitational whisper is what occasionally dislodges a chunk of ice and sends it falling sunward on a spectacular multi-million-year journey. But there may be a more active architect at work in that distant darkness. In 2016, astronomers Konstantin Batygin and Michael Brown presented a compelling celestial mystery. They analyzed the orbits of a group of extreme trans-Neptunian objects, icy bodies that swing far beyond Pluto. These orbits were not randomly oriented. Instead, they clustered in a way that suggested an unseen, massive gravity source was shepherding them, a distant perturber roughly 10 times the mass of Earth. They called this hypothetical world Planet 9. This would not be a small rocky body, but a super-Earth or a mini-Neptune, a frozen giant tracing a wildly elongated orbit that could take 10 to 20,000 years to complete. Its gravitational influence would be the hidden hand, explaining not only the orbital clustering of these distant objects, but potentially also the unusual tilt of the solar system's plane. The hunt for this ghost planet is now one of astronomy's great detective stories. Teams are using powerful telescopes like Subaru in Hawaii to scan the predicted swath of sky, a painstaking process of comparing countless images to spot a single, slow-moving dot of reflected sunlight against a backdrop of fixed stars. Finding it would be a monumental achievement, a discovery on par with the identification of Neptune in the 19th century. Yet its existence would force a profound rewrite of our solar system's history. How did a planet of that size end up in such a distant, eccentric orbit? It may have been flung outward during the solar system's chaotic early days, a remnant of dynamic planetary migrations that reshaped everything. Or it could be a captured rogue planet, an orphan from another star system that our Sun gravitationally adopted in its youth. Either scenario reveals a solar system far more dynamic and violent than our standard models suggest, with a hidden giant silently patrolling the frontier, its gentle tug dictating the fates of countless smaller worlds in the frozen dark. The hidden giant of Planet 9, if it exists, is a testament to the dynamic violence of our solar system's past, but that violence is dwarfed by the grand, slow-motion feasts occurring on a galactic scale. Our own Milky Way, that serene band of light across the night sky, is not a peaceful island universe. It is a predator, a cosmic cannibal growing larger by devouring its smaller neighbors. The evidence for this galactic diet is written across the heavens in faint, ethereal rivers of stars. For centuries, these streams were invisible, lost in the dense backdrop of the galactic disk. But with the revolutionary data from the European Space Agency's Gaia mission, which is precisely mapping the position and motion of over 1 billion stars, these stellar fossils have been pulled into sharp focus. They appear as vast, arching ribbons of stars, all moving together in coherent flows that wrap around our galaxy like the strands of a celestial spiderweb. One of the most prominent is the Sagittarius Stream. This is the dissolving corpse of the Sagittarius dwarf elliptical galaxy, a small satellite that has been in the process of being torn apart by the Milky Way's immense gravity for billions of years. As it orbits, our galaxy's tidal forces the difference in gravitational pull from one side of the small galaxy to the other, have stretched it into a long, looping river of stars that completely encircles us. We are seeing this dwarf galaxy's final act, a drawn-out stellar disintegration that will eventually see all its stars assimilated into the Milky Way's halo. An even more dramatic discovery from Gaia data is a structure nicknamed the Gaia Sausage or Gaia Enceladus. This is not a stream, but the ghost of a far more significant collision. The motion and chemical composition of millions of stars in our galaxy's halo tell a story of a cataclysm that occurred some 10 billion years ago. A massive dwarf galaxy, perhaps 1/4 the size of the young Milky Way itself, slammed into and merged with our own. The violent head-on collision did not just add stars, it fundamentally reshaped our galaxy, puffing up its central bulge and scattering stars into a chaotic, sausage-shaped distribution in velocity space, a fossilized imprint of the impact visible only in the star's movements. These stellar streams are more than just archaeological curiosities. They are chapters in our galaxy's autobiography. By studying their orbits and the ages of their stars, astronomers can reconstruct a timeline of galactic mergers, building a family tree for the Milky Way. They reveal that our home is not a pristine, isolated spiral, but a compound structure, a mosaic built from the shattered remains of countless smaller galaxies over cosmic time. This violent history also points to an inevitable future. The Milky Way's cannibalistic tendencies are leading it toward its most colossal meal yet. In approximately 4.5 billion years, our galaxy and the Andromeda Galaxy, our largest neighbor, will begin a gravitational dance that ends in a direct collision and merger. This will not be a catastrophic smash of stars. The distances between them are too vast, but a majestic billion-year-long tidal disruption. As the two galaxies intertwine, their spiral arms will be shredded, and vast new streams of stars will be flung into intergalactic space before finally settling into a single, giant elliptical galaxy. The serene Milky Way we see tonight is a snapshot in the middle of this endless cycle of construction and destruction, its beauty born from ancient violence and its fate written in the silent flow of stellar rivers. Our galaxy's violent history is written in the motions of ancient stars, but the chemical fingerprints of those same stars reveal an even deeper crack in our cosmic origin story. According to our most precise calculations, the universe's recipe is missing a key ingredient. In the first 3 minutes after the Big Bang, the cosmos was a seething nuclear furnace. As it expanded and cooled from an unimaginable heat, protons and neutrons began to fuse into the nuclei of the lightest elements. This process, known as Big Bang nucleosynthesis, produced the primordial hydrogen and helium that would fuel the first stars, along with trace amounts of two other elements, deuterium and a specific isotope, lithium-7. The physics of this brief, fiery epoch is considered a crowning achievement of modern cosmology. The predicted abundances of hydrogen, helium, and deuterium match what we observe in the oldest regions of the universe with stunning accuracy. Yet for lithium-7, the prediction fails spectacularly. The oldest stars we can find, pristine fossils from the early galaxy that should preserve the unaltered chemical mix of the Big Bang, contain only about 1/3 of the lithium our models say should be there. The universe appears to have a lithium deficit, and this is no small accounting error. It is a persistent threefold discrepancy that has resisted explanation for decades. If our understanding of those first few minutes is so precise for the other elements, why does it fall short for lithium? This conundrum forces physicists to consider two radically different possibilities. The first path leads us to new physics. Perhaps our model of the early universe is incomplete. Could unknown particles, like those predicted by supersymmetry, have been present in that primordial soup? If such particles decayed in the first few minutes, they might have altered the nuclear reaction rates just enough to produce less lithium, without disturbing the perfect agreement we see with hydrogen and helium. This would be a monumental discovery, a direct signature of physics beyond the standard model, etched into the oldest chemistry of the cosmos. The second path looks not to the birth of the universe, but to the lives of the first stars. Maybe the Big Bang did produce the expected amount of lithium, but the ancient stars themselves destroyed it. These stellar elders have deep, churning interiors. Over billions of years, could slow mixing have dragged surface lithium down into hotter layers where it was fused into other elements? Or perhaps these stars possess unusual surface activity that gradually burned the lithium away. The challenge is that these stars are so old and faint that measuring their internal processes in detail is incredibly difficult. Each potential solution has its own complications, and neither has yet solved the puzzle definitively. The lithium problem is a quiet but profound anomaly. It tells us that even our most successful stories of cosmic creation might contain a crucial missing page. Solving it could mean rewriting the first chapter of everything, or uncovering a subtle new law of nature that operated for just 3 minutes over 13 billion years ago. The lithium problem is a whisper from the universe's first moments, but some cosmic structures speak in a voice so faint we almost missed them entirely. Drifting through the dense metropolises of galaxy clusters are ghostly islands, entire galaxies that defy every expectation of size and brightness. They are called ultra-diffuse galaxies, and they are among the most enigmatic inhabitants of the cosmos. Imagine a galaxy the physical size of our Milky Way, spanning 100,000 light-years from edge to edge. Now strip away 99% of its stars. What remains is an ultra-diffuse galaxy, a vast, diaphanous cloud of starlight so faint it blends seamlessly into the blackness of space. For decades, these ghosts hid in plain sight, their light so thinly spread it was lost in the glare of the night sky and the limitations of our telescopes. Their discovery required a new kind of eye, the Dragonfly telephoto array, a revolutionary instrument built from commercially available camera lenses, was designed specifically to reject scattered light and see the faintest, smoothest structures in the universe. When it turned toward the Coma cluster, a dense swarm of thousands of galaxies, it revealed a population of these gigantic, faint smudges. They were not small. They were colossal, yet they emitted barely a whisper of light. This immediately presented a profound survival puzzle. Galaxy clusters like Coma are the most violent environments in the universe, filled with hot, turbulent gas and powerful gravitational tides as galaxies whip past one another at millions of miles per hour. Ordinary spiral galaxies entering such a maelstrom have their gas stripped away, halting star formation and often being torn apart. How, then, can these ultra-diffuse galaxies, which are as large and fragile as a soap bubble, not only exist but persist in such a punishing neighborhood? Their very survival suggests they are made of sterner, unseen stuff. The leading theory points to dark matter. An ultra-diffuse galaxy may be embedded within an incredibly massive, spread-out halo of dark matter. This invisible gravitational scaffold could hold the galaxy together, acting as a cosmic shield against the disruptive forces of the cluster. The stars themselves are just the visible tracer, the faint glitter on the surface of a deep, dark ocean of matter. But how did they form, or more accurately, fail to form? One compelling idea is that they are failed galaxies. Early in their history, they may have lost their reservoir of star-forming gas, perhaps blown away by fierce winds from newborn stars or siphoned off by interactions with other galaxies before they even entered the cluster. Without this gas, star formation sputtered to a halt, leaving behind only the dim population of stars that had already ignited, now stranded in a vast expanse. Another possibility is that their dark matter halos are somehow puffed up, their particles moving in such a way that gas never cools and condenses efficiently to form dense, star-birthing clouds. The gas remains warm and diffuse, leaving the galaxy dark. These ghostly islands force a fundamental rethink of galaxy evolution. They demonstrate that a galaxy's destiny is not dictated by its size alone, but by the complex interplay between its dark matter, its gas, and its environment. They are cosmic experiments in what happens when the recipe for a galaxy goes subtly wrong, resulting in giants that live in the shadows, their faint light a challenge to everything we thought we knew about building a universe. The ghostly islands of ultra-diffuse galaxies challenge our understanding of structure, but a more fundamental measurement threatens to unravel the very framework of cosmic history. At the heart of modern cosmology lies a single, critical number, the Hubble constant. This figure describes the current expansion rate of the universe, the speed at which galaxies are receding from us for each megaparsec of distance. Knowing this number precisely is like having the master key to the cosmos, allowing us to calculate its age, trace its evolution, and predict its ultimate fate. For decades, astronomers have refined two brilliant, independent methods to pin down this value. Yet today, these two pillars of precision disagree, and the conflict is growing into a full-blown crisis known as the Hubble tension. The first method builds a cosmic distance ladder within our local universe. Astronomers start with pulsating stars called Cepheid variables, whose intrinsic brightness is tied directly to their pulse period. By measuring their apparent brightness in nearby galaxies, we can calculate exact distances. We then use these Cepheids to calibrate the distance to even farther galaxies that host a specific, brilliant type of explosion, a Type 1, a supernova. These supernovae are standard candles. They all peak at roughly the same true brightness. By observing how dim they appear in distant galaxies, we can measure vast distances directly. Finally, by measuring how fast those distant galaxies are moving away from us, their redshift, we can calculate the expansion rate. This local measurement is meticulous and direct, and it gives us a Hubble constant of about 73 kilometers per second per megaparsec. The second method takes a completely different approach, looking back to the infant universe. It uses the detailed map of the cosmic microwave background, the ancient light from when the universe was only 380,000 years old. The subtle patterns in this light, the sizes of the hot and cold spots, act as a cosmic ruler. They tell us the exact geometry and contents of the early universe, its mix of ordinary matter, and dark energy. Using our extremely well-tested model of cosmic evolution, we can run the clock forward from that baby picture to predict what the expansion rate should be today. This early universe method is exquisitely precise, and it yields a different answer, about 67 kilometers per second per megaparsec. The difference seems small, just a few units, but in the realm of precision cosmology, it is a chasm. The uncertainty margins of each method no longer overlap. This is not an error, it is a stubborn discrepancy that has survived over a decade of increasingly sensitive observations. The Hubble tension suggests one terrifying and thrilling possibility, that our standard model of cosmology, the lambda CDM model, is incomplete. Perhaps dark energy, the mysterious force accelerating expansion, is not constant but evolved over time, changing strength in an unexpected way. Some theorists propose an episode of early dark energy, a burst that briefly turbocharged the young universe's expansion, subtly altering the starting conditions for everything that followed. Other ideas point to dark matter interacting with itself in new ways, or to neutrinos, those ghostly subatomic particles, having properties far stranger than we currently allow. This tension is more than an academic debate. It is a direct challenge to our story of reality. One of these meticulous measurements is a snapshot of the universe in its infancy. The other is a fingerprint of its current state. They should tell the same story, but they do not. Resolving this crisis will require either discovering a subtle, overlooked systematic error in our distance measurements, or welcoming a new ingredient into the cosmic recipe. The Hubble tension is a reminder that the universe is under no obligation to make sense to us, and that our greatest discoveries often begin with a number that simply refuses to add up. That stubborn discrepancy in the expansion rate forces us to confront a far deeper and more pervasive cosmic secret, one that makes up the overwhelming bulk of the universe's material content. We call it dark matter, and its true nature is perhaps the greatest unsolved puzzle in all of physics. This is not a mystery of light, but a mystery revealed by light, or more precisely, by the way light bends and moves under the influence of something we cannot see. The evidence for dark matter is not a single observation, but a converging chorus of gravitational clues. The first clear note came from the spinning of galaxies. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster and found that the visible galaxies were moving far too quickly to be held together by the gravity of the stars and gas we could see. He proposed the existence of unseen, Dunkel Materie, dark matter. Decades later, Vera Rubin provided the definitive proof by meticulously measuring the rotation curves of spiral galaxies. She expected stars on the outer edges of a galaxy, like our Sun in the Milky Way, to orbit more slowly than those near the center, just as Pluto moves more sluggishly around the Sun than Mercury does. Instead, she found that stars at the very outskirts of galaxies whip around at the same high speed as those near the core. The only logical conclusion is that each galaxy is embedded within a vast, spherical halo of invisible matter, whose gravitational pull keeps those fast-moving outer stars from flying off into the void. This dark matter halo extends far beyond the visible edge of the galaxy, a ghostly scaffold that holds the entire luminous structure together. The evidence multiplies. When we look at massive clusters of galaxies, we see their immense gravity acting as a cosmic lens, warping and magnifying the light from more distant galaxies behind them. The degree of this gravitational lensing is so extreme that it requires 6 times more mass than all the visible stars, gas, and dust in the cluster combined. Furthermore, the pattern of tiny fluctuations in the cosmic microwave background, that ancient baby picture of the universe, tells us with exquisite precision how much total matter existed in the early cosmos. The number it gives is in perfect agreement with the dark matter needed to explain galaxies and clusters today. Ordinary atoms, the stuff of stars and planets and us, make up a mere 15% of all matter. The remaining 85% is this dark, unknown substance. For decades, the leading theoretical candidate has been a class of particles known as WIMP, weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and, as their name suggests, interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. The search for WIMP has been one of the most ambitious experiments in history. Deep underground, in mines and tunnels shielded from cosmic rays, ultra-sensitive detectors filled with liquid xenon or other materials wait for the once-in-a-lifetime tremor of a WIMP striking an atomic nucleus. After decades of operation, these detectors have grown exquisitely sensitive, yet they have heard nothing but silence. The profound absence of a signal has forced physicists to broaden the hunt. Perhaps dark matter is made of actions, hypothetical ultralight particles that could behave more like a pervasive, rippling field than discrete bullets. Or maybe it consists of primordial black holes, tiny knots of gravity formed in the universe's first chaotic second, though recent observations have severely constrained this possibility. Some scientists, frustrated by the lack of a direct particle detection, have proposed a more radical solution: that we do not need dark matter at all. They suggest modifying the laws of gravity itself, a theory known as modified Newtonian dynamics, or MND. This idea can explain some galactic rotation curves, but it struggles mightily to account for the gravitational lensing in clusters and the precise data from the cosmic microwave background without invoking some form of unseen matter. The standoff is stark. On one side, an invisible substance that dominates the cosmos but refuses to show itself in our labs. On the other, a potential rewrite of fundamental physics. This is the heart of the enigma. We can map the shadow of dark matter across the universe. We can measure its gravitational grip on galaxies and the fate of the cosmos, but we still have no idea what it is. It is the silent partner in the cosmic dance, the unseen architect of every structure we see, and its identity remains the most profound, known unknown in our quest to understand reality. Dark matter's gravitational grip sculpts the cosmos, but another, even more dominant force is actively tearing it apart. In 1998, 2 independent teams of astronomers made a discovery so shocking it upended our cosmic forecast and earned them the Nobel Prize. They were measuring the distances to extremely remote Type 1, a supernova, using them as cosmic mile markers to track how the universe's expansion rate has changed over billions of years. Everyone expected to find that the expansion was slowing down, gradually braked by the collective gravitational pull of all the matter in the cosmos. The data revealed the opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than expected. The expansion of the universe is not slowing. It is accelerating. Something is actively pushing galaxies apart, a mysterious repulsive force we now call dark energy. This is not a substance like dark matter. The leading interpretation is that dark energy is a property of empty space itself, an inherent energy woven into the fabric of the cosmos. Einstein once proposed a similar concept, the cosmological constant, as a fudge factor to keep the universe static. He later called it his greatest blunder, but it may have been his greatest prescience. This energy of the vacuum exerts a negative pressure, causing space itself to stretch at an ever-increasing rate. The numbers are staggering. Dark energy constitutes about 68% of the total energy budget of the universe. Dark matter makes up 27%. Everything we see and know, all stars, planets, and galaxies, is a mere 5% floating in a sea of darkness. Yet the value of this energy density is the most perplexing detail of all. When physicists try to calculate the expected energy of the quantum vacuum from first principles, their theoretical predictions overshoot the observed value by a factor of 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the history of science. Why is the measured value of dark energy so incredibly, yet precisely, tiny but not zero? This fine-tuning is so absurd it suggests either a profound gap in our understanding of quantum gravity, or that we inhabit a universe with a very special and perhaps unlikely set of constants. Could dark energy be something more dynamic than a simple constant? Some theorists propose a model called quintessence, a cosmic field that varies over time and space. Unlike a static cosmological constant, quintessence could evolve, perhaps weakening or strengthening as the universe ages. This would change the entire expansion history and future fate. Others, facing the persistent puzzles of dark matter and dark energy, wonder if the issue is not mysterious components but a flawed foundation. Could Einstein's theory of gravity, though brilliantly successful in our solar system, break down on the scale of the entire universe? Modified gravity theories attempt to explain the acceleration without dark energy, but they struggle to match the full suite of cosmological data as cleanly. The ultimate implication of dark energy's dominance is a chilling cosmic destiny, the Big Freeze. As space expands faster and faster, distant galaxies will vanish over the cosmological horizon, their light never able to reach us. Eventually, our local group of galaxies will merge into one isolated island, surrounded by an infinite, expanding void. Star formation will cease, black holes will evaporate over unimaginable eons, and the universe will approach a state of maximum entropy, a cold, dark, and silent equilibrium. Dark energy is the engine of this desolate fate, a silent pressure in the vacuum that is writing the final, lonely chapter of everything. Dark energy writes a lonely future, but it raises a question that has haunted humanity since we first understood the stars were other suns. Given the universe's immense age and the staggering number of planets, the cosmos should be teeming with life. Yet when we listen, we hear only silence. This profound contradiction is the Fermi paradox, named for physicist Enrico Fermi, who, over a casual lunch in 1950, posed the simple, devastating question, where is everybody? The numbers are overwhelmingly on the side of existence. Our Milky Way alone contains hundreds of billions of stars, most likely orbited by planets. With so many opportunities, even if the chance of a technological civilization emerging on any given world is infinitesimally small, the galaxy should have produced thousands, perhaps millions of them. Some should have spread across the stars, their presence obvious. We see no structures, hear no broadcasts, detect no probes. The great silence is deafening, and it forces us to confront uncomfortable possibilities about our place in the universe. One of the most sobering solutions is the concept of the Great Filter. This idea suggests that the evolution of life from simple chemistry to a spacefaring civilization requires passing a series of incredibly difficult steps. Perhaps one of these steps, a barrier so severe it stops almost everyone, lies somewhere ahead of us or behind us. If it is behind us, it means the emergence of life itself, or the jump to complex multicellular organisms is a miraculous fluke. We are alone because we are the first and only to have made it this far. But if the Great Filter lies ahead of us, it is a terrifying prospect. It implies that there is some nearly insurmountable challenge that dooms all advanced civilizations before they can become visible on a galactic scale. This could be self-destruction through war or environmental collapse, the inevitable rise of a hostile artificial intelligence, or some cosmic catastrophe we have yet to foresee. Our silence would then be a warning, a sign that no one makes it to the other side. Other solutions are less apocalyptic but equally humbling. The zoo hypothesis proposes that advanced civilizations are aware of us but have chosen to place our region of space under a kind of galactic quarantine or observational preserve. They avoid contact to allow our culture to develop naturally, or perhaps they are simply waiting for us to reach a certain level of maturity before introducing themselves. In this scenario, the silence is a policy, not an absence. More practical answers focus on the sheer scale of space and time. The galaxy is over 100,000 light-years across. Even if a civilization were broadcasting, their signals might take millennia to reach us, and by then they could be long extinct. Different species might arise and fall in cosmic blinks, their lifetimes never overlapping. Or perhaps they use communication technologies we cannot even conceive of, like neutrino messaging or quantum entanglement, leaving our radio telescopes deaf to their conversations. It is also possible that interstellar travel is simply too slow, too expensive, or too dangerous to be practical. The dream of sprawling galactic empires might be a fantasy, with each civilization content to manage its own star system. The Fermi paradox is ultimately a mirror. It uses the absence of light, the lack of a signal, to force a profound self-reflection. Are we a precious rarity, the universe's first attempt at consciousness? Or are we a naive young species, blissfully unaware of the filters and dangers that lie ahead? The silence is not empty. It is filled with every possible answer, each one a story about our own destiny written in the dark. The profound silence of the cosmos is broken by a gentle, familiar glow right here in our own celestial backyard. After the last colors of sunset fade from the western sky, or just before dawn begins to brighten the east, a faint, ethereal cone of light sometimes rises from the horizon. This is the zodiacal light, a soft pyramid of illumination often mistaken for the lingering twilight. For centuries, observers across cultures have noted this mysterious shine, calling it the false dawn. Its source is not distant stars, but our local neighborhood. Sunlight is scattering off countless microscopic dust particles that fill the plane of our solar system, a vast lens-shaped cloud centered on the sun. These particles are the debris left behind from the construction and ongoing demolition of our planetary system. Dust from asteroid collisions and the crumbling trails of comets as they swing close to the sun. It is a celestial fog illuminated from within. For a phenomenon so well understood in principle, the zodiacal light holds a modern quantitative mystery. In the early 1990s, a satellite called the Cosmic Background Explorer, or COBE, was mapping the infrared sky. Its sensitive instruments measured the precise heat signature of this interplanetary dust. The data revealed a puzzling excess. The total amount of warm dust glowing in the inner solar system was significantly greater than what astronomers could account for by adding up all the known contributors, the grinding of the asteroid belt and the steady dust loss from comets. There is simply more dust out there than our inventories of asteroids and comets can explain. Where is this extra material coming from? One compelling hypothesis points to the interstellar void. Our solar system is not a sealed bubble. As we orbit the galaxy, we are constantly moving through a thin medium of gas and dust. Perhaps a steady rain of microscopic interstellar grains is drifting into our system, getting caught by the sun's gravity and joining the zodiacal cloud. This would be a continuous external source, slowly topping up the dust that is constantly falling into the sun or being blown out by solar radiation. Another, more dramatic idea suggests a recent and catastrophic local event. What if, within the last 100,000 years or so, a major asteroid collision occurred in the inner belt, or a large comet disintegrated, releasing an immense one-time pulse of fresh debris that we are still seeing the aftermath of today. The dust from such an event would not have had time to fully dissipate, creating a temporary surplus that our instruments now detect. This quiet discrepancy in a well-studied glow is a humbling lesson. It reminds us that even the space between the planets, our most local cosmic environment, is not fully catalogued or understood. We can map galaxies billions of light years away, yet we are still piecing together the complete budget of dust within our own solar system. The zodiacal light is more than a beautiful sky phenomenon, it is a forensic tool. By studying its precise brightness and composition, we are taking an inventory of the construction site of our planetary system and finding that the ledger does not quite balance. The answer may be a gentle interstellar drizzle or the echo of a forgotten cataclysm, a silent crash in the asteroid belt whose dust still shimmers in our evening sky. That gentle fog of zodiacal dust is a local mystery, but far beyond Neptune lies a boundary that feels far more deliberate, a stark edge to our solar system's construction zone. The Kuiper Belt, that distant ring of icy worlds beginning just past Neptune's orbit, was long imagined as a vast, gradually thinning field of cosmic leftovers. Instead, our telescopes have found it possesses a cliff. At a distance of roughly 50 astronomical units from the Sun, about 7.5 billion miles out, the population of detectable Kuiper Belt objects doesn't just thin out, it appears to plummet. This is the Kuiper Belt Cliff, and its existence is a direct challenge to our stories of how the solar system formed. For decades, models of the primordial solar nebula suggested the disk of icy planetesimals, the building blocks of the outer planets, should have extended smoothly for at least 100 astronomical units, fading slowly into the emptiness of interstellar space. The New Horizons spacecraft, after its historic flyby of Pluto, continued outward and found no significant increase in dust impacts, supporting the idea that the belt of small objects truly does end. This sharp cutoff is bizarre. It's as if you were walking through a forest that suddenly, cleanly stopped at an invisible fence with nothing but open plain beyond. How does a natural distribution of debris just end? One compelling explanation circles back to the ghostly gravitational hand we discussed earlier, the hypothetical planet 9. If a massive, distant planet exists on a highly elliptical orbit, its gravitational influence could have shepherded and sculpted the outer Kuiper Belt over billions of years. As it swings through its distant aphelion, its gravity could act as a cosmic plow, clearing out a vast region and pushing smaller objects into clustered, detached orbits, leaving behind a relative void just inside its closest approach to the Sun. This would create the observed cliff, with the remaining Kuiper Belt objects huddled closer in, under the protective influence of Neptune's gravity. Another, more ancient possibility involves a stellar intruder. In the Sun's earliest days, it was born in a dense stellar nursery alongside thousands of other stars. A close flyby from a sibling star, passing within a few hundred astronomical units, could have gravitationally ripped away the outer reaches of our protoplanetary disk, stripping the material beyond 50 astronomical units and hurling it into interstellar space. This would have truncated our solar system in its infancy, leaving us with a pre-cut edge that we are only now discovering. A third, simpler idea is that the primordial disk itself had a sharp edge. Perhaps the cloud of gas and dust that collapsed to form our Sun had a finite, defined size, and the process of planet formation simply used up all the material out to that boundary. Beyond it, there was never enough stuff to coagulate into significant numbers of objects, resulting in a natural, empty frontier. Each explanation paints a different portrait of our solar system's youth. A hidden planet implies a dynamic, chaotic rearrangement of giants. A stellar flyby speaks of a violent stellar neighborhood. A sharp primordial edge suggests a more orderly, isolated birth. The Kuiper Belt Cliff is a fossilized boundary, a silent testimony to an event or condition from over 4 billion years ago. By deciphering which story is written into that abrupt drop-off, we learn whether our cosmic home was shaped by internal drama, external violence, or simple, quiet isolation. Deep within the heart of our galaxy, where stars swarm in their millions around the supermassive black hole Sagittarius A star, the universe is screaming in the highest energy language it knows. The Fermi Gamma-Ray Space Telescope has been listening to that scream for over a decade, mapping the sky in gamma rays, the most energetic form of light. What it found at the galactic center was both expected and deeply puzzling. There is a brilliant, diffuse glow of gamma radiation, as anticipated from known cosmic engines like pulsars and supernova remnants. But superimposed on that expected light is a mysterious surplus, a smooth, spherical excess of gamma rays that bathes the inner galaxy in a halo of unexplained energy. This is the galactic center excess, and it has become one of the most compelling hunting grounds for the identity of dark matter. The characteristics of this excess are what make theorists lean forward. The signal is remarkably symmetrical, forming a roundish cloud centered on the galactic core, and its energy spectrum, the specific brightness at different gamma-ray energies, has a distinctive shape. For particle physicists, that shape is tantalizingly familiar. It matches what they would expect if the elusive particles of dark matter were, at long last, revealing themselves through annihilation. The theory is elegant. If dark matter is made of WIMP, those weakly interacting massive particles, they would naturally congregate in the dense gravitational well at the galaxy's heart. Occasionally, two of these particles could collide and annihilate each other, converting their mass directly into energy and producing a cascade of particles that ultimately include gamma rays. The smooth, spherical glow of the excess fits this picture perfectly, as dark matter should form a diffuse halo, not clump in discrete points like stars. The galactic center excess could be the first indirect glimpse of the universe's dominant matter finally interacting with itself. Yet in science, extraordinary claims require the exhaustion of ordinary explanations. Astrophysicists have proposed a powerful alternative, that the glow comes not from dark matter, but from a vast, unseen population of mundane but extreme stellar corpses. Thousands of millisecond pulsars, the rapidly spinning, hyper-dense remnants of dead stars, could be peppered throughout the galactic bulge. Each one is too faint for Fermi to resolve individually, but their collective gamma-ray emission could blend together into a smooth excess haze. It is the cosmic equivalent of seeing a distant city's glow on the horizon, unable to pick out individual streetlights. Another possibility points to the dormant giant at the very center. Sagittarius A star, our galaxy's supermassive black hole, may have been far more active in the relatively recent past. A past outburst, a ferocious episode of feeding, could have accelerated particles to near light speed, creating a bubble of high-energy radiation that is still fading today, contributing to the excess we now observe. Distinguishing between these possibilities is a monumental analytical challenge. The key lies in the granularity of the signal. A dark matter halo would produce an almost perfectly smooth glow. A collection of thousands of point sources like pulsars would, with enough observation time and sensitivity, eventually reveal itself as a speckled, granular texture within that glow. Astronomers are now sifting through the Fermi data with ever more sophisticated tools, looking for that telltale speckling. Some recent studies suggest a hint of such granularity, leaning toward the pulsar explanation. Others maintain the signal's smoothness holds up, keeping the dark matter hypothesis very much alive. This mystery represents a beautiful collision of disciplines, where the largest questions in particle physics are being answered by telescopes studying the center of our own galaxy. Whether it is the final sigh of ancient stars or the first light from the dark universe, the gamma-ray excess at the heart of the Milky Way is a beacon, illuminating a path toward one of science's ultimate revelations. At the galactic center, gamma rays may signal dark matter's demise, but out in the spiral arms, a more intimate and violent drama unfolds. Here, cosmic vampires are at work. They are known as black widow pulsars, and they are slowly consuming their stellar partners. In these exotic binary systems, a rapidly spinning neutron star, a pulsar, is locked in a tight, deadly orbit with a small, dim companion star. The pulsar is a SETI-sized remnant of a supernova, weighing more than our Sun but spinning hundreds of times per second. With each rotation, it beams out lighthouse-like jets of radiation and spews a relentless wind of high-energy particles. In such a close embrace, this onslaught directly bathes the companion star, slowly boiling away its outer layers and blasting the stolen material into space. It is stellar evaporation on a grand scale, a process so destructive that astronomers categorize these systems as spider pulsars, named for the arachnids known for consuming their mates. The most evolved, where the companion is reduced to a planet-sized cinder, are the black widows. Slightly earlier in the process, where the companion is more substantial but heavily irradiated and bloated, are called redbacks. The mystery deepens with the lightest of these cosmic victims. Some black widow pulsars appear to have companions with masses not of a star, but of a giant planet, perhaps just a few times the mass of Jupiter. This presents a profound puzzle of origins and survival. How could such a system form? A pulsar is born in the catastrophic collapse of a massive star, an event that should severely disrupt or even destroy any nearby orbiting bodies. One possibility is that the pulsar and its companion began as a normal binary pair of stars. After the more massive star exploded, the pulsar's intense radiation began its slow feast, stripping the companion down over billions of years from a sun-like star to a planetary remnant. We are seeing the final act of stellar cannibalism. Another, more speculative idea is that the tiny companion is not the corpse of a star at all, but a superplanet that somehow formed from the debris of the supernova itself, a second-generation world born from ashes and now enduring a hellish existence. Or perhaps it is a captured object, a rogue planet that wandered too close to the pulsar's gravitational web and was ensnared, doomed to be slowly vaporized. These extreme systems are natural laboratories for physics we cannot replicate on Earth. They allow us to study how intense radiation and particle winds interact with matter, and how gravity behaves in such a ferocious environment. Each orbit, each flicker in the companion's light as it is heated on one side, provides data. The ultimate fate of these systems is written in their decaying orbits. As the companion loses mass, the gravitational bond weakens. Eventually, the evaporation may cease, leaving the pulsar alone, or the two may merge in a final, violent event. Black widow pulsars showcase the most brutal endpoints of stellar evolution, where the dead do not rest, but instead use their furious energy to dismantle the living, atom by atom, under the glare of a billion-year-long death sentence. These cosmic vampires are the endpoint of stellar evolution, but some structures in the universe may never have even begun that process. Orbiting our Milky Way are the faintest, most diffuse galaxies we have ever found, systems so dim they are barely a smudge against the sky. Yet their motions betray an astonishing secret. According to the tug of gravity, these ultra-faint dwarf galaxies should be flying apart. The few stars they contain are moving so quickly that the meager gravitational pull from their visible matter could never hold them together. The only thing keeping them intact is the presence of a tremendous amount of invisible mass, a vast halo of dark matter. This leads to a profound and thrilling question. If a galaxy can be 99% dark matter, could there be galaxies that are 100% dark? This is the dark galaxy hypothesis, the idea that the cosmos could be littered with islands of pure dark matter, structures that collapsed under their own gravity but never managed to attract or retain enough gas to ignite the fires of star formation. They would be cosmic ghosts, massive yet completely invisible, detectable only by the subtle warping they inflict on the fabric of space-time. The primary tool for this ghost hunt is gravitational lensing. When a massive object like a galaxy cluster lies between us and a more distant light source, its gravity bends and magnifies that light like a cosmic magnifying glass. But sometimes astronomers see smaller, unexpected distortions in the background tapestry of galaxies, tiny warps that cannot be explained by the visible mass of the foreground cluster. These could be the signatures of dark matter subhalos, invisible clumps orbiting within the larger cluster. Some of these anomalous lensing events might be the fingerprints of dark galaxies, their pure gravitational presence briefly betraying them as they drift through the cosmos. Another clue comes from lonely clouds of hydrogen gas. Radio telescopes have catalogued compact, rotating clouds of neutral hydrogen, the raw fuel for stars floating in intergalactic space. In a few rare cases, these clouds show the orderly rotation of a disk galaxy, yet when astronomers point optical telescopes at the same coordinates, they see nothing. No stars, no glow, just empty darkness. These could be dark galaxies in the earliest stage of failure, pockets of gas that were never dense enough to collapse into stars, or that had their star-forming potential disrupted by external forces. Finding a definitive, uncontested dark galaxy would be a transformative moment for cosmology. It would be the ultimate confirmation of the dark matter paradigm, proving that this mysterious substance can indeed form structures all on its own, independent of the ordinary atoms that make up our world. More than a trophy, such an object would become a pristine laboratory. In a normal galaxy, the complex interplay of gas, stars, and supernova makes it incredibly difficult to study dark matter's behavior in isolation. But in a dark galaxy, the complications of normal matter are stripped away. Scientists could study how dark matter particles move and interact gravitationally with each other in a clean, quiet environment, potentially revealing whether they can collide or scatter, clues that would finally point to their fundamental identity. The hunt for these invisible islands is a search for the purest expression of the universe's hidden architecture. It asks us to accept that the cosmos may be filled with massive, silent forms we can never see, only infer from the gentle bending of light from stars billions of years older than our own. These silent, invisible islands of dark matter challenge our understanding of structure, but the largest structures we can see are now revealing a motion of their own. The cosmic web is not static. Recent studies of thousands of galaxy clusters suggest the universe's grand architecture may be slowly turning. The massive filaments that connect clusters and the dense nodes where they intersect appear to exhibit a faint but coherent rotation on scales of hundreds of millions of light years. This is not the simple orbital dance of stars within a galaxy. This is entire clusters of galaxies, each containing thousands of members participating in a vast, sluggish spin that defies easy explanation. Astronomers infer this motion by meticulously analyzing the velocity of galaxies within and around these filaments. By measuring the redshift of galaxies on one side of a filament compared to the other, they can detect a subtle shear, a hint that one flank is moving slightly toward us while the other is moving away, the hallmark signature of a cosmic whirlpool on a scale almost too large to comprehend. Generating spin or angular momentum on such a colossal scale is a monumental puzzle for cosmology. In the standard model of the universe's birth, the initial conditions from the Big Bang were almost perfectly smooth. There were no primordial whirlpools, no preferred direction of twist. The rotation we see in individual galaxies is thought to have been seeded much later by the tidal torques of neighboring protogalaxies gently pulling on each other as they collapsed. But this process operates on the scale of millions of light years, not hundreds of millions. For a filament 1 billion light years long to acquire a coherent spin, something must have imparted a twist to the fabric of space itself on a correspondingly enormous scale very early on. The standard models of structure formation struggle to account for this. It is as if you stirred a cup of coffee with a single, gentle swirl and found that the entire kitchen was slowly rotating along with it. This discrepancy points physicists back toward the universe's most mysterious first moments. Two speculative ideas from the dawn of time rise to the challenge. The first involves primordial magnetic fields. These would not be magnetic fields generated by stars or galaxies, but fields woven into the universe's fabric in its first fraction of a second, potentially during inflation or a subsequent phase transition. If such fields existed on cosmic scales, their lines of force could have acted like invisible arms, exerting a torque on the ionized plasma of the early universe. As matter flowed along these magnetic scaffolds to form filaments, it could have inherited a slow, vast rotation, a spin memory frozen into the cosmic web. The second, even more exotic candidate is the cosmic string. These are hypothetical, one-dimensional defects in space-time, theoretical cracks that may have formed as the universe cooled and underwent a phase change, much like cracks forming in ice. These strings, if they exist, would be under immense tension and could have whipped through the primordial plasma, creating swirling wakes of matter in their paths. A network of such strings could have imprinted vorticity or spin on the infant structures of the universe, setting the entire cosmic web into a slow, billion-year-long pirouette. The search for this rotation is more than a curiosity. If confirmed, it becomes a powerful new forensic tool. The specific pattern and scale of the spin could act as a probe, distinguishing between different theories of the very early universe. It could tell us whether primordial magnetic fields were real and how strong they were, or provide the first indirect evidence for cosmic strings, entities that are themselves a potential key to unifying gravity with quantum mechanics. The faint turning of galaxy clusters is a whisper from an epoch we can never directly observe, a ghostly rotation imprinted when the cosmos was a seething, energetic soup. By listening to that whisper, we are not just mapping how the universe moves today. We are decoding the conditions of its birth, reading a story of twist and torque written in the slow spin of the largest things in existence. That faint turning of the cosmic web is a subtle signature, but some marks on the ancient sky are far more blunt. In the constellation Eridanus, a sprawling river of stars, there exists a bruise on the oldest light in the universe. This is the cold spot, a region of the cosmic microwave background that is significantly colder and vastly larger than our standard models predict. It spans a staggering 1.8 billion light-years across, a colossal patch of sky where the remnant glow of the Big Bang is just a fraction cooler than the surrounding sea. The statistical odds of such an extreme feature arising from random chance in an otherwise smooth cosmos are incredibly slim, perhaps 1 in 50. This is not a minor fluctuation, it is an anomaly that demands an explanation, and the search for one has led cosmologists down two very different paths. The leading and most conservative explanation invokes a cosmic emptiness on a scale we can barely fathom. This is the supervoid hypothesis. The idea rests on a subtle but powerful effect called the integrated Sachs-Wolfe effect. As light from the cosmic microwave background travels across the universe for 13.8 billion years, it passes through the evolving cosmic web of galaxies, clusters, and vast empty spaces. When a photon enters a gravitational well like a galaxy cluster, it gains energy climbing out. But if the well itself is changing because the universe's expansion is accelerating due to dark energy, the photon can leave with a net loss or gain of energy. Traveling through a vast, growing void, a region of immense underdensity, causes the photon to lose energy, making it appear cooler when it finally reaches our telescopes. In essence, the cold spot could be a shadow cast by the largest nothing we have ever conceived. The hunt for this hypothetical supervoid has been intense. Astronomers have indeed mapped a significant underdensity of galaxies in that general direction, a void that is itself among the largest structures known. Yet here lies the core of the ongoing debate. The numbers do not quite add up. the observed void, while enormous, does not appear to be deep enough or perhaps precisely aligned enough to account for the profound coldness of the spot. The energy loss from the integrated Sachs-Wolf effect, based on our best measurements of the void's properties, seems insufficient. It is as if we found a crater, but its depth does not match the force of the impact we suspect. This persistent mismatch is what keeps more radical ideas not just alive but vigorously debated. If a natural void within our universe cannot explain the cold spot, could its origin lie outside our universe entirely? The most exotic hypothesis reaches back to the epoch of cosmic inflation, that period of hyper-rapid expansion in the universe's first fraction of a second. In many models, our entire cosmos is one bubble in a frothing multiverse, an infinite foam of expanding space-time realms. If, during inflation, our bubble universe collided or even gently brushed against a neighboring bubble, the energy of that interaction could have left a permanent imprint on our cosmic microwave background. The cold spot in this breathtaking scenario would be a cosmic birthmark, a scar from a contact with another reality. It would be the first observational hint that our universe is not alone. This deep dive into a single cold patch on an ancient map encapsulates the very heart of cosmic detective work. It is a process of iteration and relentless scrutiny. A strange signal emerges. A plausible, natural explanation is proposed and tested. When the data shows a gap, the investigation does not stop. It deepens, sometimes venturing into territories that reshape our conception of reality. The cold spot remains an open case, a quiet, cool challenge etched into the first light of everything, reminding us that some of the universe's greatest secrets are hidden not in brilliant points of light, but in the subtle shadows between them. While the cold spot is a vast cosmic shadow, another mystery glows with the vibrant geometry of a dying star's final masterpiece. Drifting in the constellation Monoceros, the unicorn, is a nebula so uniquely structured it seems sculpted by an artist rather than chaos. Astronomers call it the red rectangle, and its name is a literal description of its appearance through a telescope. This is not a billowing, chaotic cloud like many stellar nurseries or supernova remnants. Instead, it presents a stunning, nested series of bright rungs forming a hollow, rectangular frame, with dramatic X-shaped spikes of glowing gas extending from its center like the supports of a cosmic hourglass. At its heart lies a close binary star system, HD 44179, where one star has exhausted its fuel and is shedding its outer layers in a desperate, beautiful death rattle. The intense ultraviolet light from the hotter companion star excites the expanding shell of gas, causing it to fluoresce with a deep, rich crimson hue. That specific red color is a vital clue, coming not from common hydrogen but from the luminescence of complex carbon molecules known as polycyclic aromatic hydrocarbons. These are essentially soot, the same compounds found in candle smoke and automobile exhaust, forged in the atmosphere of a dying sun and set aglow in the depths of space. The true enigma, however, is not the color but the form. How does a star's death produce such a perfectly symmetrical, angular structure? In a universe dominated by spheres and spirals, the sharp corners and straight lines of the red rectangle feel profoundly unnatural. The prevailing theory focuses on the intricate dance of the two central stars. They orbit each other so closely that their gravitational interplay shapes everything. Scientists propose that the dying star is ejecting material not in a uniform sphere, but in two opposing cones or jets. These outflows are not perfectly steady, however. The gravitational tug of the companion star likely causes the jets to precess or wobble, much like a spinning top slowly tracing a circle. Over thousands of years, this wobbling jet has painted the surrounding space with a hollow, cone-shaped shell. From our vantage point, looking nearly edge-on at this double cone, we see its outline as a rectangle with an X. It is the celestial equivalent of spinning a sparkler in the dark, the persistent afterimage creating a geometric shape from a single moving point of light. Another crucial ingredient is a thick, dense torus, a donut of dust and gas girdling the binary stars at their equator. This torus acts like a nozzle, collimating and directing the stellar winds into those two precise polar outflows, while also hiding the central stars from our direct view and reflecting their light into the intricate rungs we see. Yet the precise mechanics remain elusive. What determines the exact angle of the cones? Why is the structure so crisp and well-defined over such a vast scale, spanning about 1/3 of a light year? Each rung in the rectangular ladder may represent a pulse of increased mass loss from the star, a historical record of its final millennia written in concentric shells of glowing soot. The red rectangle is more than a cosmic oddity. It is a profound reminder that symmetry and order can emerge from the most turbulent processes. It shows us that the death of a star is not merely an explosion, but a complex, layered performance where gravity, light, and stellar winds collaborate to create a temporary monument of breathtaking geometry, a final signature written in luminescent dust before fading into the interstellar dark. The red rectangle's geometric perfection is a farewell note from a dying star, but some galaxies announce their birth with a chaotic, verdant blaze. Scattered across the modern universe are tiny, brilliant objects that citizen scientists affectionately name the green peas. Discovered not by professional astronomers but by volunteers in the online Galaxy Zoo project, these galaxies are small, compact, and glow with an unmistakable, intense green hue. Their color is not from an abundance of green stars which do not exist, but from a spectacular fingerprint in their light. When astronomers split their light into a spectrum, they find an overwhelming, dominant emission line from a specific element, doubly ionized oxygen. This is oxygen atoms that have been stripped of 2 electrons, a process that requires a torrent of energetic ultraviolet radiation. That radiation can only come from a staggering number of incredibly hot newborn stars. A green pea galaxy is essentially a stellar maternity ward in overdrive, a cosmic factory where stars are being forged at a rate hundreds of times faster than in our own sedate Milky Way, all packed into a region only a few thousand light-years across. They are stellar fireworks on a galactic scale. The true wonder of these little green gems is not just their ferocious activity, but what they represent. They are living fossils, local windows into the universe's wild youth. In the early cosmos, the first galaxies were not majestic spirals, but small, chaotic clumps of gas, collapsing under gravity and igniting their first generations of stars in frantic, brilliant bursts. They were the pioneers lighting up the darkness. The green peas found right in our cosmic backyard appear to be their direct descendants, similar in size, mass, and most importantly, their frantic star-forming temperament. By studying a green pea, we are getting a close-up look at the same physical processes that dominated the universe over 10 billion years ago. This makes them invaluable laboratories. We can point our most powerful telescopes at these nearby galaxies and dissect their chemistry, their gas dynamics, and the powerful winds blowing from their stellar nurseries in detail that is impossible for their faint, ancient counterparts at the edge of observable time. This connection leads to one of cosmology's great transitional epochs, the era of reionization. After the cosmic microwave background was released, the universe settled into a dark age filled with a pervasive fog of neutral hydrogen gas. Then the first stars and galaxies switched on. Their blistering ultraviolet radiation began to tear electrons away from those neutral hydrogen atoms, reionizing the cosmic fog and clearing the way for light to travel freely across the universe once more. The green peas show us exactly how that might have happened. The furious ultraviolet output from their star-forming frenzy is so intense it blows powerful winds, ejecting material and radiation far out into intergalactic space. A universe filled with countless green pea-like galaxies would have been more than capable of flooding the cosmos with the ionizing photons needed to burn off the primordial haze. These small, green, and furious galaxies are not just curiosities. They are the missing link, the local lighthouses whose glow helps us illuminate the moment the universe woke up from its dark age and became transparent, setting the stage for everything that followed. The frantic green peas show us a universe waking up, but for decades, a crucial chapter of that awakening seemed to be missing from the story. According to our best models of cosmic evolution, the first few billion years should have been a time of explosive growth, not just for small, blue star-forming galaxies, but for colossal, dusty behemoths. These would be massive galaxies, rapidly forging stars in frenzied bursts, but shrouding their work in thick, dark cocoons of dust. Yet when we pointed our most powerful optical telescopes, like Hubble, into the deepest fields of the universe, these predicted giants were nowhere to be found. It was as if an entire population of cosmic titans had simply vanished from the record, a glaring gap in our family tree of galaxies. The solution to this disappearance lies not in the absence of the galaxies, but in the nature of their light. In these intense stellar nurseries, newborn stars are born at a staggering rate, but they are also born surrounded by the very material that formed them, vast clouds of silicate and carbon-rich dust. The brilliant ultraviolet and optical light from these hot, young stars does not escape into the void. Instead, it is absorbed by the surrounding dust grains, which heat up to temperatures of just a few tens of degrees above absolute zero. This warm dust does not glow in visible light. It re-radiates the stolen energy in the far infrared and submillimeter part of the electromagnetic spectrum, a wavelength range invisible to Hubble's keen eye. To our optical telescopes, these bustling metropolises were effectively cloaked, their brilliant starlight transformed into an infrared whisper we could not hear. They were not lost, they were hiding in plain sight, speaking a language our instruments were deaf to. The turning point came with a new generation of eyes tuned to this different light. Ground-based radio telescope arrays like the Atacama Large Millimeter Array, or ALMA, high in the Chilean desert, began scanning the deep fields. ALMA listens to the universe in millimeter and submillimeter waves, precisely the domain where warm dust glows. Suddenly, the empty patches in Hubble's deepest images came alive. Faint, blurry smudges in optical data resolved into brilliant, structured galaxies in ALMA view. These were the missing giants, detected not by their stars, but by the heat signature of the dust that shrouded them. The story expanded even further with the launch of the James Webb Space Telescope. With its giant gold-coated mirror and instruments exquisitely sensitive to infrared light, Webb can peer directly through the dust veils. It sees both the obscured stellar light that manages to leak out at longer wavelengths and the dusty structures themselves. What it has found is an abundance that has stunned astronomers. These massive, dusty galaxies are not rare anomalies. They are everywhere in the early universe, forming stars hundreds of times faster than the Milky Way does today. They are the hidden engines of cosmic dawn, building the backbone of massive galaxies we see in the modern cosmos at a breakneck pace. This profound shift in perspective solves one mystery while teaching us a deeper lesson about cosmic humility. For years, we were constructing a history of the universe based primarily on the light we could easily see. It was like trying to understand a bustling city at night using only a flashlight, completely missing the vast factories humming with activity in the darkened industrial district. The discovery of this hidden population rewrites the early chapters of galaxy formation, revealing an epoch far more dynamic and dusty than we ever imagined. It underscores a fundamental truth in our exploration of the cosmos. The universe reveals its secrets only in the light we choose or are finally able to see. Every new window we open, every unfamiliar wavelength we learn to interpret, can unveil an entirely new layer of reality, turning missing chapters into the central plot of our cosmic story. Globular clusters are the retirement homes of the Milky Way, ancient spherical swarms where stars have aged together for over 10 billion years. Within these serene gatherings, we expect to see only cool, red giants and fading white dwarfs, a uniform population of stellar elders. Yet scattered among them are brilliant, hot, blue stars burning with a youthful intensity that defies time itself. Astronomers call them blue stragglers, and their very existence is a paradox written in Starlight. They are stragglers because they appear to lag behind in the aging process, blazing with the blue-white heat of a star in its prime, seemingly billions of years younger than every other star surrounding them. It is as if you walked into a room filled exclusively with centenarians and found a handful of vibrant 30-year-olds laughing among them. How can a star be born long after the party ended? The answer lies in the extreme social dynamics of a globular cluster. These are not peaceful places. A typical cluster's core is a stellar metropolis of unimaginable density, with stars packed 1,000,000 times more tightly than in our sun's neighborhood. In such a crowded dance, close encounters and even direct collisions are not just possible, they are inevitable over billions of years. This violence provides the first path to creating a blue straggler. When two ordinary, aging stars collide and merge, their hydrogen fuel cores mix. The new, more massive star that results burns hotter and bluer, effectively resetting its clock. It is not truly young, but it wears the disguise of youth, a stellar phoenix born from a catastrophic merger. The second path is more insidious and patient. Many stars in the universe are born in binary pairs. In the dense core of a globular cluster, these pairs can be driven even closer together by gravitational interactions with neighbors. In such a tight embrace, one star can begin to act as a cosmic vampire. As the more massive star ages first and expands into a red giant, its outer layers become gravitationally vulnerable. Its smaller but hotter companion star can siphon off this hydrogen-rich material, pulling it onto its own surface. This fresh fuel stokes the companion's nuclear furnace, causing it to grow more massive, hotter, and bluer while the donor star is stripped down to its core. The vampire star is rejuvenated, its life extended by consuming its partner. Both theories reveal a universe where stars are not isolated islands. Their life stories can be dramatically rewritten by companionship and catastrophe. By studying the light and orbits of blue stragglers, astronomers can distinguish between these origins. A straggler born from a merger will often spin rapidly, a legacy of the colossal collision. One born from mass transfer may still be found orbiting a tiny, depleted white dwarf, the ghost of its former companion. These brilliant blue anomalies are more than just stellar oddities. They are forensic evidence. They tell us about the dynamic history of the cluster itself, recording the frequency of collisions and the fate of binary systems over cosmic time. They prove that even in the oldest neighborhoods of our galaxy, there is no true stillness, only a slow-motion ballet of gravity, theft, and rebirth, where stars can steal fire from one another to cheat the relentless march of time. Geminga's story begins not with a rhythmic radio pulse, but with a silent, brilliant glare. In the early 1970s, a satellite designed to monitor nuclear tests, named SAS-2, detected a powerful source of gamma rays in the constellation Gemini. It was one of the brightest gamma-ray objects in the sky, yet when astronomers pointed their radio telescopes toward that exact spot, they heard nothing. No ticking, no beeping, just the empty hiss of interstellar space. For 2 decades, this object, catalogued as Gemini gamma-ray source and nicknamed Geminga, was a profound enigma. What kind of cosmic engine could produce such ferocious high-energy light without the telltale radio signature of a pulsar? The mystery endured until 1991, when the Einstein Observatory finally detected a faint, flickering X-ray source at the same location. The flicker had a precise period. It pulsed 4.2 times every second. Geminga was not silent. It was screaming in a language we had been deaf to. It was a pulsar, a city-sized neutron star spinning furiously on its axis, but its lighthouse beam of radiation was not aimed at us in radio waves. Instead, its narrow, powerful beam of gamma rays swept across our line of sight with each rotation, making it appear as a steady, brilliant source. This was a revolutionary revelation. For the first time, we had found a neutron star that was radio quiet. Its discovery solved a 20-year-old puzzle while simultaneously exposing a vast observational bias. Our census of these stellar corpses had been built almost entirely by listening for their radio pulses. Geminga proved that many neutron stars could be broadcasting their existence exclusively in higher energy light, invisible to our radio surveys. They were cosmic lighthouses with colored filters, some shining radio white, others glowing in gamma-ray blue, and we had only been looking for the white ones. Located a mere 800 light-years away, Geminga is one of the closest known neutron stars to Earth. Its proximity allows us to study its environment in stunning detail, revealing a spectacle of its motion. As it rockets through space at over 200,000 miles per hour, it plows into the thin interstellar medium. The result is a magnificent bow-shock nebula, a cosmic wave of energized particles that glows in X-rays, shaped exactly like the bow wave of a ship cutting through water. This visible wake confirms its high speed and direction, painting a picture of a stellar cannonball fired from an ancient supernova, now on a lonely journey through the galactic sea. The reason for its radio silence remains an active topic of study. It may be that its magnetic field is aligned in such a way that the radio beam simply never points toward Earth while its gamma-ray beam does. Or perhaps the processes near its surface that generate radio emission are intrinsically weaker or absent in this particular object, channeling the star's rotational energy almost entirely into gamma rays and its powerful particle wind. Geminga taught us a fundamental lesson about the universe. Our view is always limited by the tools we use. By opening a new window, the gamma-ray sky, we found an entire population of hidden pulsars that had been there all along, silently marking time in the darkness. They are the ghosts in the neutron star graveyard, reminding us that for every cosmic signal we hear, there may be a dozen others whispering in a light we cannot see. That single handwritten "wow" in the margin of a data printout became more than an anomaly. It became a catalyst, a symbol of the tantalizing possibility that we are not alone. In the decades since, the search for extraterrestrial intelligence has evolved from a lonely radio ear listening to static into a vast, multidisciplinary scientific endeavor, scanning the ancient light of the cosmos with tools and concepts the astronomers of 1977 could scarcely have dreamed of. The core question remains the same: are we the universe's only conscious listeners? But the strategies for finding an answer have exploded in both scope and sophistication. We are no longer just listening, we are watching, analyzing, and thinking in entirely new dimensions. The traditional search for deliberate radio broadcasts like the one hypothesized for the WOW signal continues with unprecedented power. Projects like Breakthrough Listen represent a quantum leap. Funded by private philanthropy, it is the most comprehensive search ever undertaken, using some of the world's most powerful radio telescopes like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. Its goal is monumental: to systematically survey the 1 million closest stars to Earth, the entire galactic plane, and even 100 nearby galaxies. It is listening across a broad range of frequencies, analyzing the data with supercomputers for any signal that stands out from the natural cosmic noise, any pattern that whispers of artificial origin. This is SETI at industrial scale, a methodical, data-driven sweep of our celestial neighborhood, but the modern search has fundamentally expanded its vision beyond radio waves. We now actively look for the flash of a cosmic lighthouse. This is optical SETI, which scans the heavens for brief, powerful pulses of laser light. The reasoning is elegant. An advanced civilization might find it more efficient to send a tightly focused, extremely bright laser pulse to another star rather than a diffuse radio broadcast. A laser beacon could, in theory, outshine its host star for a fraction of a second. Telescopes equipped with ultra-fast photometers are now monitoring thousands of stars, looking for that telltale, unnatural spike of light, a deliberate flare meant to catch our eye across the light years. Perhaps the most profound shift is the hunt for indirect evidence, the cosmic archaeology of technology. Scientists now search for technosignatures, the unintended byproducts or colossal footprints a civilization might leave on its environment, detectable across interstellar distances. We are not just listening for a hello, we are looking for the smog of an industrial world. By analyzing the atmospheres of exoplanets with telescopes like the James Webb Space Telescope, astronomers can search for chemical imbalances. A planet with extreme levels of artificial pollutants like chlorofluorocarbons, or an abundance of oxygen alongside methane in proportions that biology alone cannot sustain, could point to technological activity. We are also looking up for the shadows of engineering on a staggering scale. The search for megastructures like the hypothetical Dyson swarm that once seemed to explain Tabby's star is now a formal part of the technosignature portfolio. By combing through data from planet-hunting missions like Kepler and TESS, scientists look for stars with bizarre, non-periodic dimming patterns that no natural dust cloud or planet could create, the potential signature of vast artificial constructions orbiting a sun. The legacy of the WOW signal is not an answer but a sustained, evolving question. It taught us the importance of patience and the necessity of looking in new ways. That 72-second tone, whether it was a cosmic mirage or a genuine call we failed to answer, ignited a fire. It proved that the universe is capable of producing signals that stop us in our tracks, that defy our immediate explanation. Today, that fire fuels a search that is broader, deeper, and more ingenious than ever before. It is a search conducted not in despair over the great silence, but with the quiet determination of a new generation of scientists who understand that the oldest light traveling to us might still carry a message. They are sifting through the whispers of galaxies, the spectra of alien atmospheres, and the flickers of a billion stars, knowing that the next WOW could be written not in red pen on a chart, but in the silent, definitive language of data, a single point of light or a curious molecule that changes our story forever. From the echo of the Big Bang to the silent question of alien signals, our journey through 30 cosmic mysteries has spanned the breadth of space and time. We have traced the faint glow of the universe's first light, felt the ghostly pull of dark matter, and listened for whispers in the static between the stars. Each enigma, from the cold spot's chilling shadow to the frantic flicker of a fast radio burst, represents a frontier of human understanding. Some, like the pioneer anomaly, have been solved through meticulous earthly detective work. Others, like the nature of dark energy or the truth behind the Hubble tension, remain wide open, challenging the very foundations of our cosmic models. What binds them all together is not a single answer, but a single, enduring human trait, our relentless curiosity. For millennia, we have looked up at the night sky and seen not just points of light, but stories. We have learned to read those stories in the language of physics, using mathematics and engineering to translate the ancient light traveling for billions of years to reach our eyes. Every mystery solved expands the boundaries of science, forcing us to invent new technologies, conceive new theories, and see the universe in a radically new way. Every mystery that persists is an invitation, a cosmic puzzle waiting for its solver. This is the grand project of our species, to decode the narrative of existence itself, written across the canvas of the cosmos in photons and gravitational waves. So the next time you find yourself beneath a clear night sky, remember this: that ancient light falling on your eyes carries secrets from the dawn of time and the farthest reaches of space. You are part of the story, a conscious node in a universe trying to understand itself. Stay curious, wonder about the shadows between the stars. The next great discovery, the key to unlocking one of these profound mysteries, could be just one telescope observation, one brilliant insight away. The universe is speaking. We are learning to listen. If this journey through cosmic mysteries sparked your imagination, let us know in the comments below. Share your own favorite cosmic puzzle and join us as we continue to explore the wonders written in ancient light.